But let's start out with the classic question of, are there any questions besides the one I just asked? All right. Ready? If I have a positive charge here, what can you tell me about the electric field?
It's going in all directions. It's going in all directions.
Be more, okay, I'll agree with that. Can we add some more detail?
Can you say that the positive charge is radiating out?
Okay, not only in all directions, but radiating out from it. How do you know it's going away? Or is this a case of Daniel got us this far, so someone else pick up the mantle?
Because
All
the
right.
electric field points away from the proton.
Or more generally, the positive charge. All right. How many lines should you draw?
Several.
How many? Seven?
Several.
Several, okay. Until you get tired. All right. And if I got a negative charge here, what can you tell me about the electric field because of the negative charge?
Pointing towards it.
Okay. And as a general rule, if it's a single charge like that, drawing so that you have some symmetry is generally preferred. So if I have a positive and negative charge, both of them, what's the electric field smack dab in the middle?
Pointing to the right,
Why pointing to the right?
because it should point in the direction of the negative
Oh,
charge.
yes, and because the question I asked, I was thinking something different, and yes, it is pointing to the right. Because they're both pointing to the right there. What about right here? What's the direction of the electric field? All right, so I got one gesture this way and one gesture, I think, this way, another gesture that way.
Depends on if they're equal or not, and then if that's, you know,
If what are equal?
the positive and the negative, if they're,
Let's assume that they have equal magnitudes, just opposite signs.
Did you specify the charge? You said it was a charge, right?
Yes, got some positive and negative, we can make it more specific, positive Q and negative Q.
Right. The dot that you just drew though, is that,
At some point in space.
oh,
With electric field, we don't need to have another charge
charge, yeah.
there. Because we're claiming the electric field exists even if there's nothing in that spot. All right, so we had still 2 votes for this way and then 1 down.
kind of like across, maybe, something like going this way.
All right. Assuming I've drawn it correctly. Is this closer to the negative charge or positive charge?
Closer to the negative.
Negative.
All right, so that will be the dominant electric field, is from the negative charge. It's not gonna get rid of the positive charge, it's not like they fight it out, duel to the death and negative wins, but it is gonna be closer to that than it is to that. Because at this point, we have 2 electric fields. I have one pointing this way, and then I have one pointing that way. So if I needed to find the electric field, let's assume I gave you some distances here. So I told you, well, you know what, let's do it this way. Let's make this 13 centimeters. 5 centimeters. And 4 centimeters. And the Q equal to 3 microcoulombs. Megacoulombs. Mathematically, it's just a factor of 1,000. I was trying to come up with numbers that where scientific notation was optional. So how would I find the electric field at this point? Or more importantly, how would you find it?
Law of cosines.
Probably don't need to use law of cosines in this particular case. But I'm sure you could find a way to put it in there if you needed to.
Since we know like what the right triangle is, we can use Pareto's theorem.
Okay.
But
And
that doesn't
the-
find,
Oh, I see what you mean. Oh,
that finds like the length of the,
so what exactly are you asking? I'm sorry.
I want to find the electric field at this point.
So the electric field, don't we measure it as, E equals 2K EP over, radius?
Wasn't that the infinite line of charge?
Oh, no.
the electric field would it be like 2ke over r cubed? And then
Yeah.
times the momentum?
Say it again.
I was just reiterating the formula for electric field.
Okay.
2ke over r cubed times momentum.
All right. So KEQ over R squared.
I think it's r cubed. Or-
Oh. I see what's going on here. Yeah, the formula that Daniel gave and the one that I think you're using the same formula, that's for an electric dipole.
Okay.
Now, the assumption in the electric dipole was that the distance you are away from it was much larger than the distance between the two charges. This is not significantly larger than that,
Got it.
or actually that. So the dipole formula does not apply here.
Okay.
Do we just need to find the resultant vector between the two vectors that you've roughly drawn?
Yes. So, the electric field at, we'll call it point P, is the electric field at point P from the positive charge plus the electric field at point P from the negative charge. We did something very similar last week or the week before, at some point in our past. And to find it from the positive side, or from the plus charge, we got that formula right there. KEQ over R squared, R positive hat, and then negative let's see, minus KEQ over R squared, R negative hat. Because it's going towards the negative charge. Now somebody's already answered this question, it just at the wrong time. How do we find R? I guess that's R positive and R negative. Or describe to me where R positive is in my incredibly beautiful drawing.
Would it be the 13 centimeters plus the 4 centimeters because that's the distance between the charges?
It is not.
Pythagorean theorem.
That's the time to throw in Pythagorean theorem. What are we Pythagorean theorizing?
particle, right? You wanna see like where it is in that space?
Is it gonna be
The-
sorry.
Give me specifics, what am I squaring and adding?
Oh, 13 and the
And the
5
five.
centimeters.
All right. R positive is the distance from my charge to where where we're concerned, which is at point P. So this distance right here, that's R positive, which is the square root of 13 squared plus 5 squared. Now, the reason I chose 13 and 5 is because originally I was going to do a Pythagorean triplet here, and then after I'd already written it down, I realized 12 and 5 create a Pythagorean triplet, not 13 and 5. But that's okay anyway, because the other side is 4 and 5, and that's not a triplet either. So what is R positive? Or actually, what I care about is R positive squared. So that would be 169 and 25.
194.
Okay. So R positive squared is 194. What's R negative squared?
41.
Now, some students, when faced with this, will actually, what we need is R squared, but some students will go ahead and do the square root, round off, and then square it again later, come up with a slightly different value. Just please be aware, done extra steps and come up with a less accurate answer. So we can now plug and chug. However, we are dealing with, well, first off, units. What are the units of this 194?
Centimeters.
Centimeters
Yep.
squared.
And we want to be cool. So 1.94 meters squared, actually. Oh, centimeters squared. Centimeters to meters, 2 spaces, but we have centimeters squared, so we have to do it again. And so this would be 0.0041 square meters. So we have to deal with R plus, this directional thing. How do we need to get a common system here. Now, if we really want to, we could probably force in law of cosines. I don't think that's the simplest way in this particular case. What's an alternate way, instead of using law of sines, law of cosines, how else could we solve this?
I was gonna say like side angle side or something like that, but that finds an angle, not the charge. So like electric field there.
So we have side angle side. So the side angle side, side angle side.
Yeah, trying to find like that angle, but that angle wouldn't tell you that doesn't really make sense.
It actually does.
Oh, it does, okay.
I mean, but again, depends on the approach that you're gonna take here. My personal recommendation, get these into rectangular form. If I plug into KQ over R squared, I'm gonna get the magnitude of the electric field, but I need to somehow be able to add it to this one right here, so I need a common system. And so, in rectangular form, we'll just go with traditional I hat, J hat. That angle there is this angle here, assuming that this dotted line is parallel to that dotted line. In a similar manner, this angle here is going to be the same as this angle here. So let's do it. We just throw out this, which trig function should we use to find the first angle? What I will cleverly call theta plus. This one's theta minus.
Use sine. Use sine.
Sine?
Yeah, sine of theta plus.
So the sine of theta plus is equal to 5 over the square root of 194.
So it might be better to do, it might be better to, oh wait. Never mind, go ahead.
There's a I mean, you can do this without any loss. Potentially without any loss.
Yeah, I was gonna say maybe tangent would be better, so you can do opposite, and use both of the.
Traditionally, you would go with the ones where you know the numbers, because that square root of 194 is going to be rounded off. 5/13 is also going to be rounded off by your calculator. So, pre-calculator days, you definitely would use the 5 and the 13. So, we could also use the arctan of 5/13. And what is that angle?
About 21 degrees.
And theta minus? Now, I haven't seen enough students do these type of things. If you got an answer under 45 degrees, then you should, I would hope, go, wait a second, something's not right. Because the opposite is larger than the adjacent, we should be getting something bigger than 45 degrees here. All right, so now my problem has been reduced to, I guess, whatever that is. So let's actually find that. Remember that K, the abbreviated, is 9E9 times Q, which I said was 3E negative 9, and then divide by our R squared there. This is the magnitude of E plus. I feel like someone's got the answer and they're just afraid to say it.
1391.8.
1391.8, okay? Now, we don't need units at this point, but what are the units? And let me throw two questions out there. We got the one I just asked about what are the units, and the second one is, did anyone else get the same number?
I just got that, yeah.
Okay, so we have two people.
Yeah, I did as well.
Okay,
Is this the newtons per coulomb?
it is newtons per coulomb. The magnitude of E minus. And I think I commented on this in the first semester course, but for two of you, putting the absolute value symbols around it means I'm looking for the magnitude. Some textbooks won't use the single absolute value symbol, but for vectors, they'll use the double line. So in case you're looking at other sources and they use the double line, that means the same thing as what I'm using, the single lines.
Double ones.
Go ahead.
Just to make sure the double one's vector. What do you say that one was?
When you do the double lines, you're looking for the magnitude of the vector. Some textbooks will do this to represent magnitude of the vector, and I'm doing this to represent magnitude of the vector.
Oh, okay.
This is just in case you happen to see the
Got it.
double lines on each side, it means the same thing as magnitude of.
Got it.
All right, so E negative,
That's 6,585 points.
6,585.
Yeah.
Is that-
0.4.
Point four.
Is that also nano-coulombs?
Wrong unit, misspoke.
I said, is that also nano-coulombs?
You said nano?
Oh, sorry, I saw the N and I was like, sorry. What was it, Newton-coulomb?
I think you'll have to word out.
It's per coulomb.
Yeah, per. I don't know if you said per or not.
No, I didn't, no.
Okay, newtons per coulomb.
Okay.
Now, just on the surface of it, this makes some sense because we already established it's closer to the negative charge, so the electric field from the negative charge should be a larger magnitude, should have a larger magnitude. And it does. So something seems right. So, as I was saying before, we've now reduced the problem to the electric field at point P. We're adding 1391.8 newtons per coulomb at an angle of something I just erased. That was the old room, I could still probably read what I erased. What was the angle for this? What was theta plus?
21.
21?
21 degrees.
Plus 6585.4 newtons per coulomb. Negative 51.3 degrees. Because it's below the positive x-axis. Or if you prefer, add 360 degrees and come out with a positive angle there. So we reduced it down to just the addition of two vectors that are currently in polar notation. Because finding the magnitude was relatively easy, finding the direction took different steps, but not too horrible an operation. And so now it comes down to how do you add the vectors?